Okay, this is the lecture video for MAC1114 trigonometry. We're in section 7.3, and in this section we're going to be looking at how to solve various types of trigonometric equations. First degree equations, second degree equations, and all the methods that entails. Mainly what I believe you may need review on is how to deal with solving second degree equations, because there are many methods. There's taking the square root of each side when there is no linear term. You can do that when there's a second degree term and a constant. There is all the various types of factoring, so that needs to be reviewed. And then there's just the main concept of what we're looking for when we ask for the solution for a trig equation. What you see on the first first 2 pages, is just a review of your algebra skills, how to solve second degree equations, which was the main emphasis of the course right before this, but I will continue to review that with you each time I get to anything that is second degree. Okay, so we'll start with the first degree equations, get you used to what specific solutions are, what general solutions are, all of that. What's on the first 2 pages I'm going to be going over as I do the problems. It's just, solving techniques. Okay, so here's the first problem. It says the equation sine of theta equal to 2 has a real solution that can be found using a calculator. So in section 7.2 and 7.1 we were practicing the inverse of each of the trig functions, and we even had some problems in each section where we were actually using our calculator, as this problem asks for, in order to find a solution. And that requires just you turning this around and writing it as an inverse statement. So this written as an inverse statement would just be inverse of 2. All you do is switch these 2 items right here to go from non-inverse to inverse, or vice versa. Okay, so this states, you're going to answer true or false, that there will be a solution that you can find using your calculator, and you're about to find that. If your calculator quits on you, that means there is no solution to this. And just moving ahead, I don't know if you remember this, but from section 7.1, where we were looking at inverses, we specifically talked about what is the allowable domain values for your inverse. And this number has to be between -1 and 1 in order for the inverse to exist. So you can expect your calculator to cut out on you. It's not going to be able to find the solution, but here it is anyway. So it's second. Now you're in radians here. It changes this. Okay, I'm already in radians, so let me quit out of here. So second, inverse, put in the 2. See, it's too big. Error on the domain. So is there a real, this says, has a real solution that can be found. That would be false. Okay, example 2. If all solutions of a trigonometric function are given by the general formula pi over 3 plus 2 pi times a multiplier k, or you can get other solutions for that very same equation by 10 pi over 3 plus 2 pi times k. K is a multiplier where you can plug in different values for k based on what is mentioned in the solution. Where k is, and here they go telling you what k is, where k is any integer. So it could be 0, 1, 2, 3. So now this says, which of the following is not a solution? Not a solution. Okay, so all we can do is start generating some solutions. I'll do a few with this equation, a few with this equation, and let's see if we can figure out which one is not a solution. Okay, so using the equation pi over 3 plus 2 pi times k. Pi over 3 plus 2 pi times k. And first I'm going to let k be equal to 0. Okay, so this is for k equal to 0. Okay, so this would be theta equal to pi over 3. This would be 0, so this would just be pi over 3. That's my first solution using this equation. This time I allowed the k value to be 0. Okay, then, and let's see, why don't I just arrange it this way, because then I can use the other equation down here. Okay, so that's one of the solutions. Okay, so now the second solution, using that same equation, I'm going to go theta is equal to pi over 3, but this time I'm going to let the k value be 1. So first I allowed the k value to be 0, now I'm allowing it to be 1, and in this case theta ends up being, now you can use your calculator here, you can go 1/3, you don't need to enter the pi, just the coefficients of pi if you want to get your calculator to help you. If you can do it in your head, that's fine. So you would enter 1/3, don't enter the pi, plus 2. Don't enter the pi. 1/3 plus 2 if you need help from your calculator. 1/3 plus 2, and instead of enter, press math, enter, enter. It'll combine those fractions, giving them a common denominator and simplifying it. So calculator gave me 7/3 pi. Let's do another answer from this equation using this first equation right here, and then we'll get some solutions and see if we can rule out what is and what isn't a solution. So pi over 3, this time I'm going to let the k value be 2. And that gives me a little help from the calculator. 1/3, that's the coefficient of this pi term. And then the coefficient of this term would be 2 times 2, 4. That's all of that would be the coefficient of this pi term. So 1/3 plus 4. 1 divided by 3 plus 4, math, enter, enter, 13/3. So you can see the increments that they're jumping in. This is 1/3. This is 7/3. When you go from 1/3 to 7/3, you're jumping 6/3. When you go from 7/3 to 13/3, you're adding another 6 in the numerator. So 1 plus 6 gave you 7. 7 plus 6 gave you 13. So that you don't have to keep plugging into this whole thing. You know that there's a pattern here. Like for instance, the next one would be 19/3. Okay, so let's see what kind, we're not going to pick yet. Let's see what kind of solutions we get from the other equation. The other equation is 10/3 pi plus 2k pi. And again, you can let that k value be any integer. So here would be one solution from that equation. You would go 10/3 of a pi plus 2 times pi. You can put the k in the middle or at the end, doesn't matter. I'm going to let k be equal to 0. That is what I'm doing for this particular solution, and I get theta is just equal to, this would zero out, leaving you with just 10/3. So 10/3. Okay, there's one solution. I can get another solution by going 10 pi over 3 plus 2 pi. This time I'll let k be equal to 1. And you might want to get your calculator to help out with that arithmetic. It would be 10/3 plus 2. Put everything in except the pi term. So 10/3 and then 2 times 1 is 2. Don't put the pi in. 10/3 plus 2. And then hit math. The math key is in the first column, 3 keys down. Enter twice. 16/3. Okay, and you can keep going here also. You can also see a pattern here. I mean, if you want to do one more, 10 pi over 3 plus 2 pi. This time I'll let the k value be 2. And that gives me theta is equal to 10/3 plus 4 pi, but don't enter the pi, just the 10/3 and the 4. And that is 22/3. Okay, so all these solutions are some form of thirds. And notice that, once again, you're adding 6 for each numerator. This one started with 10/3, add 6 to that numerator, you jump to 16/3. Add 6 to that numerator, you jump to 22/3. So if you did have to go any further out, you could do so without work. So let's see, which of these answers are skipped over? Like for instance, we got 22/3, we got 13/3. Could we possibly get 28/3? Well, each of these have a difference of 6 in their numerator. So the next answer here, if we would have went a little bit further, would have been 28/3. So this is also a solution. This is the one that is not a solution. So just a little practice at learning how to use a general solution for an equation. You didn't solve that, nor did you come up with the solution, but you're learning how to plug into one. So kind of baby steps towards finding your own solutions. Okay, example 3. Suppose that theta equal to pi over 2 is the only solution for a trigonometric equation and theta is between 0 and 2 pi. Assuming a period of 2 pi, which means the solutions repeat every 2 pi, every time you move or rotate a distance of 2 pi. Which of the formulas gives all the solutions of the equation? So that would be this. Okay, so if the period is 2 pi, that means you want a 2 pi rotator. And you can write it like this if you want with the k at the end, where you're saying the first solution is right here. And that if you rotate all the way around the circle and make yourself land right back on pi over 2, which would take some form of a 2 pi rotation. So this k value, by you letting the k value be various integers, where k can be 0, it can be 1, it can be 2, it can be, and all that's going to happen is you're just going to keep landing right on this same spot, picking up the same x and y coordinate. So this is what we call a general solution. And what you see back here is the rotator that makes you keep landing right back on the original solution. So that is this solution right here. Okay, moving to example 4. In example 4, we start to find our own solutions. And we start off with first degree equations in examples 4, 5, 6. And then moving to the next page. So 4 through 7 are first degree equations. So whenever you have a first degree equation, the technique for solving is to isolate the variable. You just isolate the unknown. Whereas when it's second degree, there are many ways to solve a second degree equation. You have several types of factoring methods that will handle that. You have the square root method, you have the quadratic formula, so much more involved when it's second degree. So isolate the unknown. Now this time, instead of the unknown just being an x as it was in your algebra classes, now it's a trig expression. So this is the unknown here, and we're going to try and isolate this trig word, this trig expression, sine of theta. Okay, just like when you were in your algebra classes, you remove anything that is added or subtracted first, by going like this, or you can just move, show that you're moving it to the other side with the arrow, at which point it would become a -6. So at this point you would have 2. 6's would cancel, the +6 and the -6. You'd have 2 sine of theta is equal to 5 take away 6, -1. And then you would divide off that coefficient always as your last step, whether you're just solving with x's or whether you're solving with trig words. So this would be gone, leaving you with sine of theta equal to -1/2. So let me make the comment that you did this over and over again in section 7.1, because you would be presented with an inverse to begin with. You would then rewrite it in this form, and you would try and draw a triangle where the sine value were these numbers, making yourself move into the quadrant that has this kind of sign for the sine trig function, and you would come up with the various solutions, which had to do with your reference angle, but ultimately had to do with where the hypotenuse of the right triangle is. So you're going to be doing that all over again, only without restrictions. The only thing that restriction is, you're not restricted in the sense that you were restricted in section 6.1, where you can only spin through 2 quadrants. Here they're telling you, give us any answers that occur from 0 to 2 pi. Because when they want you to give all the solutions that the equation has, they'll say, give the general form of the equation. And you just saw us working with what's called the general form of an equation. A general form equation is a way of giving us solutions for all solutions for a particular equation. And it generates infinite number of solutions. They're not asking you for that. They're just saying, give us whatever solutions occur between 0 and 2 pi. Okay, so number 1, notice that you want your sine to be negative. Sine is the y value. The y value can only be negative down here and down here. And I think you've seen me draw these triangles enough at this point that you realize that, hopefully, that where I'm putting these arms right here, I'm really drawing the hypotenuse of a triangle. Okay, always, after I decided what quadrants to rotate into based on me wanting my sine value, which is really the y value, wanting that to be negative and knowing that y values are negative down here, I then quickly make a triangle out of each of these by just traveling from the end of this arm, which is really the hypotenuse, to the nearest x-axis. Okay, then I always place this where it belongs. If the sine is the y value, then it belongs on the vertical leg, because the vertical leg of your triangles ever since chapter 6 have played the role of the y variable, or what we call the sine value. Okay, and I would put the values right here, but they simply don't matter. The vertical leg is what matters with respect to the reference angle. Always across from the vertical leg is the reference angle. Okay, the reference angle associated with 1/2 is 30 degrees. Now, see how it says solve the equation in the interval 0 to 2 pi? Because they're using radian type numbers here, you will give your final answer, which is an angle, or could be several angles. You will give that in radian form. So always associated with or across from a leg that is 1/2, whether it's negative or positive is irrelevant, is 30 degrees. 30 degrees is the same thing as pi over 6. If this reference angle is pi over 6, then so is this one. But your job, just as it was in section 7.1 and 7.2, is to find the final theta. The reference angle only leads us into the final theta. So I have very much stressed what this has to do with this. Okay, now this time, as opposed to section 7.1 and 7.2, you're allowed to rotate from 0 in a counterclockwise fashion. You're not worried about being restricted to just two quadrants with your spinning. You could have spun all throughout from 0 to 2 pi. It's just that we're in these quadrants simply because the sign is negative in these two quadrants. So the question becomes, how far do I have to rotate from 0 in a positive manner to get to this particular value? Same thing for this one. You want to give both of these answers. I mean, you're not skipping over one of them. I don't want to make it seem like that's what's happening. You really want to give both of these answers. Give this one as our first solution. We'll give this one as our second solution. Okay, so if I was rotating from here to here, let's think in sixes. When you're at the 1 pi location, if you want to relate everything to sixes, this would be 6 sixes. Also mark this other landmark. When we first start right here on the x-axis, it's called 0, but it can also be called 2 pi. In terms of sixes, 2 pi is the same thing as 12 sixes. 12 divided by 6 is 2 pi. Just this number is double that one. Very simple. So when you're rotating, you would have rotated to 6 sixes, but then this arm, you rotated an additional 6. So one of your solutions is 7 pi over 6. Then to get to this arm from 0, you'd be rotating all the way almost to 12 over 6, but stopping 1/6 before you got there. So you'd be rotating, 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 all the way till you got here. You would have stopped 1/6 before you got there. Therefore, this is 11 sixes. And those are your two solutions. 7 sixes and 11 sixes. And they'll probably just ask you to list all your solutions and separate them by commas. That's typical in the software that you are probably using. Okay, solve the equation between 0 and 2 pi. We're still looking at linear equations. So here we're going to isolate the variable, which is sine of theta, just like we did in the first problem. Move all numbers away from it. So I'm going to move this to the other side. That's the same thing as adding 1 and adding 1. So this will be sine of theta is equal to 1. Okay, then you're asking yourself, at what angle do we have a sine value of 1? So when you are talking about zeros and ones for the sine or cosine function, you're talking about being on the unit circle at some quadrantal location. Quadrantal just means you're right on an axis, either the positive x-axis or positive y or negative x or negative y. One of those places is going to have a sine value of 1. One of those angles. We want to know at what angle does this occur. So let's just review here. If you're in a unit circle, the radius is 1. So this particular location at 0 degrees, or you can just call it 0 if you're talking in radians, which they do want you to do. Coordinates are 1, 0. You have to remember that this first number, the x value, is considered the cosine, and the second value is considered the sine, all the way around. And you're looking for the location. It's either here, 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 or here. It's one of these four where the sine value is 1. And I guess you can imagine that it is where I'm going to move right now. Up here at pi over 2, or 90 degrees, the coordinates are 0 for x and your 1 for y. Again, this is cosine, this is sine. So this is the one that satisfies what you're looking for. At the pi over 2 location, you have a positive 1 in the sine position. And I'm just going to list the other two just to review with you. At pi, the coordinates are negative 1, positive 0. So here the sine value is 0, not what we want. This is 1 pi over 2, 2 pi over 2, 3 pi over 2. Each quadrant is a half a pi. So this place has the coordinates of your 1 down. So that's your y coordinate. So once again, This is not a place where the sine value is 1. So there was only one place where the sine value was 1, and that was right here. You have a sine value of 1, and so the angular location that we seek, theta, in other words, the solution to this equation is theta equal to pi over 2. Okay, moving to number 6. Okay, in problem number 6, we're going to be looking for where we have a tan value of -1, and that would happen because of this. This is a first degree equation. We're trying to isolate the trig word because that's the technique when you're solving first degree. So I'm going to move this over here, and that puts me in this situation that I just verbalized. We're looking for where is the tan value equal to -1. Now you may already know what the reference angle is. Students, about this point in the course, they start to, or a little bit sooner, they start to realize that when you're in a 45-degree triangle, both legs are equal, square root of 2 over 2. So when you go y over x, you end up getting a 1. It is the one kind of triangle that will get you a tan value of 1. So we want to get a -1. We want to be in a quad. We're asking ourselves, what quad gives tan values that are negative? Well, think about it. Tan's y over x. Only way that this is y over x is ever going to come out negative is if either the y is negative while the x is positive, or the x is negative while the y is positive. You can't have both of them being negative, and obviously you can't have both of them being positive because otherwise you won't satisfy this. So we're trying to get into a quadrant where the tan value is negative, and we most definitely want a reference angle of 45 degrees, but I'm going to state that 45 degrees in terms of radians because of these directions. Okay, so where is the tan negative? Definitely not there. There's no negatives here. Here the y's are positive while x's are negative, so tan would be negative here. You could also use that little saying, all students take calculus to know where certain trig functions are negative and where they're positive. In this quadrant here, you would have negative x's and negative y. The tan can't possibly be negative there, but it is negative over here. So you can be in this quadrant right here, and you can also be in this quadrant right here. Okay, in order to complete the triangle, let me move these out of the way because they're just, I always end up writing something right where I don't want it. Thank God for erasers. Okay, so. All right, so let's go down to the nearest x-axis, close up that triangle. Likewise right here, go close up your triangle. We talked about the reference angle being 45 degrees because in that situation, both legs are square root of 2 over 2. Just so happens, though, that in the quadrants that you have chosen, one of the values is negative. Like this is your y value, the vertical leg. This is the x value. X's happen to be negative here. So you would definitely get a tan value of -1. You would have this y over this x resulting in a -1. Likewise, the same thing would happen here. Only here, the y is negative, the vertical leg, while the x is positive when you're over here. So you would still get a -1 for tan. Y over x, you get a 1 with a negative. And that's again because we've decided that this reference angle had to be 45 degrees so that you would have square root of 2 over 2 on both legs, with one of them being negative based on the quadrant that you chose. So, again, let me keep stressing that when you are giving your final answer, you are saying where the theta is. And that is something that has been reinforced throughout this whole chapter. Where this hypotenuse is, that's your final, those are your final solutions. all that the reference angles do is allow you to get that final answer. Okay, so we'll call this our first solution. How much would you have to rotate from 0 to get to here? Well, let's think in force because the reference angle's in force. So this is the 1 pi location, also known as 4 force. Over here where 0 is, this is well, when you're first on it, it's 0, but if you go all the way around, it's 2 pi, which is the same thing as 8 force. So if you know what each of these landmarks is in terms of the same denominator that the reference angle is in, then you will be much more successful at coming up with these actual final solutions in quadrant 2 and quadrant 4. Okay, so if you were rotating towards 4 force, but you stopped 1/4 before you got there, this stopped just short of that, and you stopped 1/4 before you got there, then this has to be 3 pi over 4. Okay, that's one of your final solutions. Again, the reference angle's pi over 4. Just get you to those answers. If you were to continue rotating until you were getting very close to 8 force, but you stopped once again 1/4 before you got to 8 force, you would be at 7 force. Okay, and those are your 2 solutions. In these quadrants, the tan values were negative, and the triangles drawn using the reference angles that we came up with produced a tan value of -1. So your solutions are 3 fourths and pi over 4. Okay, moving on to example 7. In example 7, one more linear equation. We're trying to solve for this unknown secant of theta, and there's 2 things to move. We need to move the 2 over here, and we also need to move the multiplier. The multiplier is always moved last, just like when you're solving an equation with x's in it. So we're going to move this over here. It becomes -2. You then have 6 here while having 3 secant of theta right here. Divide off that 3, divide off that 3, and you're looking for when is secant equal to 2. Okay, so secant equal to 2. Let's decide what quadrant we want to be in. Your secant is really, it's defined like this. It's related to cosine. Cosine's x over r, with the r being 1, and this is r over x. Now the r is always positive, so when you're trying to determine how you're going to make something positive or negative, you need to be looking at the x's or the y's. The way that this is going to be positive is if you're in a quadrant where x is positive. So secant is positive in quad 1, and secant is positive. Again, I'm probably putting this right where I want to draw. Let me move it over. So secant is positive here, secant is positive here. Okay. All right, so now if you want to figure out what the reference angle is, you could get a little help from your calculator. And this was, again, something we talked about in previous sections. In fact, it was in section 7.2, how the calculator could help to get that reference angle. So why don't we do that? You can't do inverse secant per se because you don't have a key for that, but so instead of doing this, I mean, what you want to do is you want to find, and I'm going to have to move this up here. Okay, so just to get some calculator help, if I was able to find the inverse of 2, that would be my theta. Because you know that you can change any non-inverse statement into an inverse statement just by switching these two, which is what I just did at the top of the page. Okay, I went inverse secant, and I'm putting the 2 up against the secant theta over here. But then we were discussing in section 7.2 that there's really no key to do this, so there's got to be a way of rewriting this. And what we talked about is that you could use the reciprocal function of secant, but in its inverse form. Reciprocal function of secant is cosine. Here it is in its inverse form, as long as you do the reciprocal of this domain value as well. So by putting this in the calculator, you're really finding the inverse of 2, which will be the angle associated with this value. So let's press this in. And you might want to have it in degrees at this point, because if it starts spitting out radians, you're not going to recognize them. So I'm going to put my mode in degrees, and then I'm going to let my calculator help me out. Second inverse cosine, I'm going to put inverse cosine of 0.5, which is 1/2, and it gives me 60 degrees, which is the same thing as pi over 3, because they don't want me to give my final answers. It's just that if I'm going to allow the calculator to help me, I'm not going to recognize the angular help that it is giving me unless it's in degrees. Okay, so this situation of secant being equal to 2 is associated with a reference angle of 60 degrees. Okay, so this reference angle right here is 60 degrees, also known as pi over 3. And this reference angle is the same thing. Whatever the reference angle is in one quadrant, it's the same in both quadrants. So now remember, you are looking for where the hypotenuse has rotated to. In quadrant 1, this hypotenuse or final theta will always be exactly the same as the reference angle. But in no other quadrant is that true. So in this quadrant, theta is, well, we got to think about this now. Our reference angles are in thirds, so you want to think about these landmarks. I mean, not necessarily 1 pi because everything's happening over here, but definitely 2 pi. 2 pi is the same thing as 6/3. So if you were rotating from 0 to try and get to where this other hypotenuse is, the one that's in quad 4, you would have been rotating all the way till you almost got to 6/3, but stopping. This arm stopped 1/3 before it got to 6/3. Therefore, this answer is, in quadrant 4, is 5/3. So we have a 1/3 pi, and we have 5/3 pi for our solutions. And I'll just kind of highlight those so you know what of all this work is the actual solution. Okay, now we finally get to second degree equations. And you can see the very first equation that we have a second degree term and a constant. If that be the case, you have just a second degree term and you just have a constant besides that, but you don't have the unknown in any term raised to the first degree like you did in these other problems. That's perfect for the square root method. And a constant. Okay, second degree term and a constant. I'm going to use square root method. And you know, as soon as you start moving into second degree, you're talking more answers. First degree, you're not going to have as many answers, but second degree, because you're going to get plus or minus when you use square root method, that will give you the opportunity for more answers. So again, we're going to, before taking the square root, first isolate the unknown. Okay, so that means I'm going to be moving this over here, leaving me with 6 sine squared theta equal to 3. Then I'm going to divide by 6, leaving me with sine squared theta equal to 1/2. Then I'm going to get rid of the square. But on the numeric side, anytime you are working with even types of roots, like odd roots are cube root, fifth root, seventh root, but when this index is an even number, like square root, when it's a square root, they don't write the number there, but it's said to be a 2. Fourth root, sixth root, those are even roots. And anytime you are working with an even root, you are to report both the positive and the negative root on the numeric side. Even roots have a positive and a negative root. So don't forget that. So this square root gets rid of the square on the sine. So now you have sine of theta is equal to plus or minus square root of 1 on the top is just 1. And then square root of the bottom number looks like this. And if you rationalize that, you may begin to recognize that these are the legs. This is one of the legs associated with, well, both of them are the same, with 45-degree reference angle. So this is square root of 2 over 2. And the reference angle that goes with that is 45 degrees, or in other words, pi over 4. Since we're giving our answers in radian form based on these instructions. They talk about solving it over the interval 0 to 2 pi. They want your answer in pi form. Okay, so we can be in a quadrant where we're either having for our sine value either positive square root of 2 over 2 as that vertical leg, because the sine is associated with the y value. In other words, the vertical leg on the triangle. So look, that could be any one of 4 places. I could draw my triangle like this. I'm just going to draw Chris because I'm going to draw 4 triangles here. So I could draw my triangle like this and let that vertical leg be square root of 2 over 2. It's allowed to be either, this is always the sine value. This vertical leg, also known as the y coordinate, is also known as the sine. Sine and y are synonymous. So since I'm allowed to have that vertical leg either positive square root of 2 over 2 or negative square root of 2, these would be the 2 quadrants where that sine value is positive square root of 2 over 2. And in these other quadrants, you have the vertical leg being negative square root of 2 over 2 because y values are negative here. But regardless of whether those vertical legs are positive square root of 2 or negative square root of 2, across from any kind of square root of 2 over 2 is a reference angle of 45. So this reference angle and every single one of these 4 reference angles is pi over 4. But each one gives a different final answer. So let's take this under consideration. The most important thing in this class that will not stop evolving in almost every single section is the reference angle and how it's related to the final answers that you're giving that are associated with those reference angles. That is the main theme here. Okay, so trying to figure out what each of the thetas are. They are where the hypotenuse is in each of these quadrants. So I want to know where each one is. I'm going to give 4 different solutions. Okay, all related to pi over 4. So this will be my first solution. Final theta, when you're in quadrant 1, is equivalent to the reference angle. So my solution in quadrant 1, pi over 4. Second answer. Okay, I'll take you through the ropes again. Eventually you'll start doing this on your own. This is 1 pi Same thing as 4/4. So when I'm doing this answer right here, I'm thinking about that 4/4 and how if I rotated from 0 all the way to where this blue arm is right here in quadrant 2, that would be 3/4 because you almost made it to 4/4, which would have been the 1 pi mark, but you stopped. This arm stops 1/4 before getting to 4/4. So it is 3/4. So there's a solution, here's a solution, and then likewise if you're at 4/4 and then you go 1/4 beyond it, then you have this answer in quadrant 3, which is 5/4. It's 1/4 beyond the 1 pi mark, which was 4/4. So 4/4 plus 1/4, 5/4. Third answer. Fourth answer. Now you are on your way back to 0, which the first time you're on it, when you take off originally, it's called 0, but then by the time you come back around, as you're spinning around again, it then becomes called 2 pi. Well, with respect to force, that's 8/4. So where this blue arm is in quadrant 4 is 7/4. This arm stopped 1/4 before getting to 8/4. So that is your fourth solution. Okay, so second degree equation, the method was, for solving, was the square root method. I isolated the variable, then I took the square root of each side, recognized what I was getting was square root of 2/2, but I'm allowed to go anywhere where it was either positive or negative for the sine value. I was looking for this, and therefore we came up with having a reference angle of square root of 2/2. But, you know, again, if you're not sure about that, you can do what we did in sections 7.1 and 7.2. You could have just went inverse of square root of 2/2, and you would have seen that your calculator would tell you 45 degrees. Okay. Moving on to number 9. Now we're working with a double angle. Those kind of problems, whenever it's a multiple angle, either 2 theta, 3 theta, 4 theta, there's, you know, some few extra steps here. Okay, so this one starts off with you rewriting the problem without the double angle. Work it without the double angle for right now. I'll tell you when to drag it back in. Now this says without the double, that you are to find the answers between 0 and 2 pi. So I'm going to show you something after I rewrite this. So solve it as though it's just sine of regular theta equal to square root of 3/2, which you've been working with already in all those linear examples that we had. So there's two places where this 2 theta gets dragged into the problem. First of all, it doubles up your domain. If they're saying they were, you know, saying in the original instructions that you find the answers between 0 and 2 pi, but you're working with 2 theta. So that doubles the number in the middle, and therefore it doubles these tail end numbers. So you're multiplying that entire domain interval by 2. So 2 times 0, 0. 2 times 2 pi, 4 pi. This just means that you're allowed to spin around the circle twice. You may spin around twice, finding any solutions within that double revolution that you can. Okay, so we're allowed to spin more than once around the circle. Everything we've done so far, you were allowed to spin around just 1 full revolution. Now we can spin up to 2 full revolutions. So let's go ahead and find those first 2 answers, and then we'll just spin right back to both of them and get our third and our fourth answer since we're allowed an additional revolution. Okay, so let's see. So we're looking for this to happen. We want to know where is the sine value, which is really just the y value. When is the sine value equal to square root of 3/2? And we want it to be negative. So you want to know where is the sign negative. In other words, where are the y values negative? So here's my picture. Okay. So my sine values are negative down here and also over here. And if you want to go ahead and put that value on the vertical leg, which is where the y value always goes. Okay, y value, sine value, same thing. Okay, likewise over here, go ahead and put that value right here. And because you have a value on the vertical leg, you don't need to worry about any values here because the vertical leg is what tells you the reference angle, and the reference angle leads into the final theta. Okay, the angle always across from square root of 3 over 2, which is considered the long leg in a long leg, short leg scenario, because if one of the legs is square root of 3 over 2, the other one's 1/2. This one's called the long leg. The other one would be the short leg. So always across from the long leg is 60 degrees, also known as pi over 3 in radians. So this reference angle's pi over 3. Those reference angles lead us into two of our semi-solutions. Even what I'm doing now is not going to be the final solutions. If it wasn't a double angle, it would be. But you're now into this kind of problem for the very first time. There are some extra steps. I'm going to lead you through all of them. So this right here, this is a semi-solution. It is not a full-on solution yet. Okay, so the theta associated with this, I'll call this the second one. And this will be the first one because I'm going to hit this one first. So the theta associated with this one right here being that the 1 pi location is thought of as 3/3. Thirds because the reference angle's in thirds. So if you were rotating to 3/3 and then went an extra third, this would be called 4/3 of a pi. If you continued to rotate until you were almost at 2 pi, which is known as 6/3, so if you were continuing to rotate but you stopped 1/3 before you got to 6/3, then this would be known as 5/3 of a pi. And those would be the two semi-solutions if you were only allowed to rotate around the circle one time, but you're allowed to rotate 2 full revolutions. So you've already gotten back to 2 pi. Now spin around again, but they're going to have new names. If you were on this angle right here called 4/3 and you rotated all the way back around and back to the 4/3 again, that would just give you a third solution. It would be where you started off standing, revolve around 2 pi, and you get a new name for this location. You can get your calculator to help. I was demonstrating this in other problems. Just put the coefficients in there, 4/3 plus 2. And you'll get that you have another semi-solution. 4/3 plus 2 would be 4/3 plus 2. Math, enter to help with those fractions. So 10/3 is another semi-solution. Okay, now let's get one more here. If you were on 5/3, but you're allowed to rotate an additional time so that you want to land right back on these arms, which are the only locations that there are actually solutions. If they've given you permission to rotate more than once, and if there was a 3 theta here, then you'd be allowed to rotate around 3 times. But because of the 2, you can rotate around twice. So you hit this solution the first time, but then you can rotate and land right back on it again. Same thing here. So the other solution that goes right here, we'll call it the fourth solution, would be where you're standing originally, 5 pi over 3, and then allowing yourself to completely rotate around an additional 2 pi. And you can again get that from your calculator by just entering 5/3 plus 2 and hitting math, enter. 5/3 plus 2, math, enter, and you get 11/3. Okay, so now to finish the problem, now we're going to get the final solutions. And here's where the 2 theta also plays in. It allows you extra revolutions in finding your answers, which allow you to get extra answers. But then also, the only way that you can plug into this, multiply it by 2, and the sine of that value be equal to square root of 3 over 2, is if you, or negative square root of 3 over 2, is if you take each of these semi-solutions and set it equal to 2 theta. So that will be our last step. Okay, so it's going to be 2 theta equal to this first solution, 4 pi over 3. Then divide by 2. And when you divide by 2, that's the same thing as multiplying by 1/2. So on this side, I'm just going to do it that way. I'm dividing by 2 on both sides, but over here I'm just showing it as multiplication by 1/2. So this ends up being 4 pi over 6, which reduces to 2/3. That is your first final answer. And what I just did with that solution, that semi-solution called 4/3, you're going to do that with each of your semi-solutions. Okay, so next one, 2 theta equal to the other semi-solution at that location, which was 10 pi over 3. Divide by 2 here, divide by 2 on the other side, and you get theta is equal to, what would this be, 10 pi over 6? Top times top is 10 pi, 6, but by the time you reduce it, 2 goes into the top 5 times, 2 goes into the bottom 3 times. So 5/3 pi is also an answer. Okay, and now for my third and fourth answer. Okay, I take my 2 theta, use this other semi-solution, 5 pi over 3. Divide by 2, divide by 2. And you get theta, because these 2's cancel, 5 pi over 6. That's my third solution. And then last one, 2 theta equal to that fourth semi-solution. These are semi-solutions here, this one and this one. And these were semi-solutions. So 2 theta equal to 11 pi over 3. Divide by 2. Do it on the other side as well, but I've run out of room, so I'll have to write it here. 11 pi over 3. Divide by 2, divide by 2. Same thing as multiplying by 1/2. So that final solution is 11 pi, top times top. 3 times 2 gives you a denominator of 6. Okay, so third and fourth final answer. So those are the most serious ones because you have to find the semi-solutions and then you have to find the final solutions. You have to remember that whatever the multiplier is, that controls how many full revolutions you're allowed to take around the circle in order to pick up your answers. Once you find the original solutions, you're just rotating right back to those same locations with as many allowable revolutions as you've been permitted. Okay, that is number 9. Okay, so example number 10. Solve the equation, give a general formula for all solutions, and then list 6 of the solutions. Okay, so if you're looking for where sine of theta is equal to square root of 2, okay, notice that sine is positive. Sine is the y coordinate. It's even defined as y over r, but r is 1. So sine is positive, in other words, the y coordinate is positive in quad 1. And if this is square root of 2 over 2, and sine is positive in quad 2. Y's are positive here, y's are positive here. And that y value, or sine value as they call it, always gets placed on the vertical leg. The vertical leg tells you what the reference angle is, which would be 45 degrees. Okay, so make that same reference angle in both triangles. Then give the theta associated with each hypotenuse. This theta would be, remember, the theta and the theta prime always match when you're in quadrant 1. But they do not match once you leave quadrant 1. So the theta that goes with this is, again, that thing with the fractions. This is 1 pi or 4/4. I'm talking in force because the denominator of the reference angle is in force. So to rotate from 0 to where this hypotenuse is, stopping 1/4 before you got to 4/4, you're at 3/4. Okay, so there. Now we're going to make general solutions out of these two solutions that we've gotten. General solutions are where you give an equation that has a rotator on it that allows you to keep rotating back to these places where the original locations were. Okay, so in this problem, give me 1 second. Okay, so for the solutions that are in quad 1, it would be, this is an equation that will generate repetitive solutions in quad 1. Pi over 4, and then if you rotate 2 pi, you'll land right back on that same arm repetitively. So 2 pi times k, and you can put the k right after the 2 or right at the end. So you're saying that k can be any integer, 0 or 1 or 2 or 3, on and on and on, any integer. So if you put a 0 in there, it would be pi over 4 plus 0, that means you're there the original time. When you put a 1 in there, that means you're rotating 1 additional time, but still landing here, thus resulting in the same values and the same reference angle. Okay, the one that's in the general solutions that are in quad 2. And then we're going to get answers with these general solutions. Okay, that one starts off with a 3 pi over 4. Okay, you're going by this right here. This one started with a pi over 4. This one starts with 3 pi over 4. Start off your general solution with the theta that corresponds to the hypotenuse. And then if you rotate full revolution 2 pi as many times as you want, where again k could be equal to 0, 1, 2, blah, 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 blah. Then you could get answers over and over again by making yourself land in on the same arm each time. So now if you want to do the rest of this where it says list 6 solutions, we'll give 3 that are in quad 1. See if I can get some of it done up here. So quad 1, using the equations, like the first couple of problems in this section, they gave you the general solutions and you just practiced using them. Now we have created them ourselves. We've moved to that point where we can create the general equations ourselves and know how to use them to get specific solutions. So working for solutions in quad 1, pi over 4 plus 2 pi k rotator. Pi over 4 plus 2 pi. First I let k be equal to 0, which would just result in, this would be 0 plus pi over 4. Pi over 4, we already knew that that was a solution. And then each time you're adding 2 pi. So this would be pi over 4, the next one, plus 2 pi times, and this time I'll let k be equal to 1. So that would be 1/4 plus 2. And you can get your calculator to help if you like. 1 divided by 4 plus 2, math, enter, enter, and you have 9/4. That's another solution in quad 1. And then one more, because it says we have to get 6. Now I'm going to do pi over 4 plus that 2 pi rotator, rotating 3 revolutions this time. Or no, 2. I skipped over that one. So first I rotated not at all. That just gave me the original solution. Then I did one additional full revolution. Now I'm doing 2 additional full revolutions. Okay, so this would be 1/4, don't put the pi in your calculator, plus 4 as the coefficients for pi. So 1 divided by 4 plus 4, and hit math, enter, enter. And you get 17/4 of a pi. Okay, there's 3 solutions for quad 1, and now I'm going to get 3 solutions for quad 2 using the other equation that I generated. So the other equation is 3/4 pi plus that 2 pi rotator, k, letting k be equal to 0, 1, 2, 3, so on, is how many extra times you're rotating. This represents the original solution. Here's another one. 3/4 plus, this time I'll go 2 pi times 1 additional revolution, landing right back on that same arm. So that'll be 3 divided by 4 plus 2. And hit math, enter, enter, and you have 11/4. And then 3 pi over 4 plus 2 pi, let the rotator, the k value be 2 this time, so it'd be 3/4 plus 4. Oops. Okay, so we came up with 2 general solutions and then generated 6 solutions with those general equations. 6 specific solutions. Okay, and number 11. Okay, problem number 11. I do not think I have enough room here, so I'm going to do this on paper. Just grab some paper real quick. Okay, so we're looking for sine of 2 theta is equal to square root of 3 over 2. We're looking for the general formula and 6 solutions. So we're doing what we did in example 10, but with a double angle. And this is example 11. Okay, give me one moment. Okay. Okay, so with these, I was telling you that the first thing that you should do is rewrite it without the double angle. And just respond to finding the thetas associated with that. And we had a positive square root of 3 over 2. Okay, so just here's a picture of that situation. When you want your sine value to be positive, as you see right here, that's the same thing as saying you want your y value to be positive. Therefore, you can be right in this quadrant or right in this quadrant. Okay, you can come right down to the x-axis to close up those triangles, and you can put this value where sine values always belong, on the vertical leg. So square root of 3 over 2, square root of 3 over 2. Okay, this is considered the long leg, where one of the legs is square root of 3 over 2 and the other one's 1/2. It's just that we don't need the horizontal legs because the vertical leg tells what the reference angle is, and as soon as you have the reference angle, you can go in for the semi-solutions. So always across from this long leg is your 60-degree angle. Okay, so one of your semi-solutions, because remember, we're going to come up with a general solution here, so that'll allow you to rotate more and more. You can rotate infinitely with the general solution. So this solution, final theta, where the hypotenuse is the same as the reference angle when you're in quadrant 1, but not in this other quadrant. So this is just pi over 3. We're going to work that into our final general solutions, and then we also want to talk about the theta associated with this hypotenuse. And this one would be, this is the 3/3 mark. We're talking thirds now because of the way the reference angle has a denominator of 3. So if you were rotating from here to where this hypotenuse is, that's 2/3. Okay, so now we want to give general solutions for these semi-solutions that we've gotten. So what we do is we come over here now, and using what I got in quadrant 1, so I'll label that right here. This is for quad 1, the solutions in quad 1. You want 2 theta, the double angle, to be equal to pi over 3 plus a 2 pi rotator. Because standing on this original arm at pi over 3, but then rotating right back around again, which would take an additional rotation of 2 pi times k, because you can, the k is so that you can let it be various values, which allow you to rotate around more than once, landing on this leg over and over again. You do 1 revolution because k is 1, you land here again. You do 2 revolutions, you land right back here again, over and over again. We want that situation where we're putting a revolver, a rotator added on to this original position. We want that to be equal to 2 theta. You drag the 2 theta into it right now. And so then if you simplify this, if you take this entire equation with a value on the left side and these 2 values on the right side and divide the whole thing by 2, that means you have 3 different things you're dividing by 2. 2 theta divided by 2 is 1 theta. Okay, now these are the solutions in quadrant 1. Pi over 3 divided by 2 looks like this. Same thing as pi over 3 times 1/2. And 2 pi k divided by 2, just this 2 divided by this 2 would cancel, leaving you with pi times k. So those solutions in quadrant 1 Those angular solutions are pi over 6 with a 1 pi rotator, the k value being the rotator because it can take on different values. K can be 0, 1, 2, 3, etc. Okay, then the solutions in quad 2. Okay, so the solutions that were in quad 2 were like this. Original location in quad 2 was 2/3 pi. And if you want to repeatedly land on that same arm, because you may not land anywhere except on your original arms that are highlighted in blue by rotating successively more and more revolutions. So if you rotate 2 pi times however many times you're going to rotate, you can just keep landing right back there. But we want 2 theta to be equal to this situation. So solutions in quadrant 2, because you're supposed to report your solutions as just theta, not 2 theta. You want this to be equal to 2 theta, but then you're going to divide this entire thing by 2. You're going to divide that term by 2, that term by 2, this term by 2. So 2 theta divided by 2, theta. These are solutions in quad 2. 2/3, whoops, what did I just do here? 2/3, I put pi too many times. I've got an eraser here. Okay, so 2 pi over 3 divided by 2 is the same thing as 2 pi over 3 times 1/2. These would cancel, leaving you with pi over 3. And then 2 pi k divided by 2, this 2 would cancel with this, leaving you with just pi times k. Okay, so this is general solutions for everything in quad 2. These were general solutions for everything in quad 1. And then I believe this problem asked you to actually list 6 solutions. So you can get like 3 solutions for each of those general equations that we just came up with. Okay, so I'll do that part right now. Okay, so 3 solutions from this first equation would just be when you let k be equal to 0, that would just be pi over 6 plus pi times 0, pi over 6. Okay, that's one of your solutions. When you go to get the next one, it's just pi over 6 plus pi times 1, which is pi over 6 plus 1 pi. Not that I needed to write that again. If you want to put that in your calculator, it's 1/6 plus 6 sixes, which is 7 sixes. But you can get your calculator to help. Okay, one more. We're going to get 3 off of each of these general solutions. You could also do pi over 6, and you could put a rotator of 2 where you're rotating around twice. So this would be pi over 6 plus 2 pi, and you can put that in your calculator, 1/6 plus 2. But this is 12 sixes, and 1/6 is 13 sixes. And if you get 3 more solutions for a total of 6, you could get the other 3 off of this other general equation. So this would be pi over 3. And again, you let the k values be 0, then 1, then 2, on and on and on. We're just looking for 3 solutions. We already have the first one, because if we put a 0 right there in this other equation, if you put a 0 there, that gets rid of this term, leaving you with just pi over 3. So pi over 3 is the first original solution. If you rotate around 2 pi, it would be pi over 3. Oh no, rotating, we're plugging into just this, not 2 pi. So rotating pi times, put a 1 in there, would just be 1 pi. So 1/3 plus 3/3 right here would be 4/3. And then one more time, pi over 3 plus pi, and this time I'll put in a 2. So this would be 2 pi. Put a 2 in there and it'll be 2 pi. So this would be 1/3 plus 6/3, which is 7/3. Okay, so this is what you'd be feeding into whatever software you're using to do the homework. This is one set of solutions right here. General equation for everything that happens in quadrant 1. This is the general equation for everything that happens in quad 2. These were 3 solutions generated using the equation for quad 1. And these were 3 solutions generated by the equation that we got for quad 2. Right? Tons of work. Okay, moving on to next problem, which is example 12. This one says use a calculator. So in example 12, we were doing this, use a calculator to solve the equation. You know that you can get this angle, which was the whole point of section 7.1, just by turning this into an inverse. Go inverse. All that's required to go from non-inverse to inverse is to switch these 2 items. That was the first thing we did for almost every problem in section 7.1 where we were using these inverses. So it's inverse sine, put the 0.52 right up against the sine, now it's an inverse, and the theta swings out and takes its place. Okay, so now you're going to go put that in your calculator. Now I believe they're letting you give decimals for these. This is not going to be something that's a special right triangle, so you can make sure that you're in radian mode. Let me check this out. My mode is in degrees. Switch to radians. Quit. And go ahead and put that in. So second, inverse sine 0.52. Close it. And you have 0.55 as one of the solutions. So that calculator is giving you the reference angle. Now let's talk about what quadrants we want to be in. We want to be where the sine is positive. They're showing a positive sine value here, which is the same thing as saying you want to be in quads where the y is positive. The sine is y. So you could be right in here with your answer. You could be right in here. Now I'm not even going to bother to close up these triangles because they're not special right triangles. I really just need the reference angle, which will then tell me where this rotating arm is. I mean, you can close it up if you want it to seem, just like what we were doing, because it is what we're doing. We know that the reference angle, sine is positive in this quadrant and sine is positive in this quadrant, because sine is just the y value. So we found out that this was 0.55 according to our calculator when we did inverse sine of 0.52. We got that angle of 0.55. So that would be the reference angle in both of these. But we want to know where the theta is. In quad 1, the theta is the same thing as the reference angle. So that's a final answer. And then in this quadrant, Okay. How far do you have to spin to get to this arm? So you have to think about this landmark right here. Now I'm not going to turn it into any kind of a fraction because we're not dealing with reference angles that are fractions. Just leave it in decimal form. Talk about it as pi. So the discussion is this. You were traveling on your way to pi but never quite made it there. You stopped this much short of making it to pi. So this answer here would be 1 pi minus the angle that you did not pass through. You stopped before passing through it. So you're going to subtract off the 0.55. So that second function, let me just clear second function, call it that pi symbol and subtract the 0.55. And you get 2.59 because you're doing it. Go to the second decimal place with these answers. They probably stated that, will state that somewhere. They'll tell you what place to round to. So yeah, let me put my answers up here. So this is 2.59 for this theta right here, and then this theta was 0.55. Okay, so those are your final answers. 0.55, quad 1, and 2.59 is the angle, but in radian form, in quad 2. Okay, moving on now to number 13. In problem number 13, we're looking at secant is equal to a negative. So we're going to ask ourselves, in what quadrant is the secant value equal to a negative? Where is the secant value negative? Just remember, secant's defined as r over x. Well, the hypotenuse is always positive. So for the secant to be negative, it's because the x is negative. That's really what this means. If this can't ever contribute any negativity to the scene of creating a secant value because it's always positive, then it would have to be this that causes it to be negative. So if secant is negative, it's because x is negative. Just repeating what I'm saying. Hopefully that makes sense. Okay, so now let's go to where the x's are negative, and that would be over here. X's are negative over here. X's are negative over here. Now, if you want your calculator to show you what to do with that particular situation, you can get involved with the calculator, and you can go like this. If you're starting off with secant of some angle is equal to negative a little break there. And you want to know what the angle is, then you can do inverse secant. Inverse secants find us the angles. Just switch these two items. However, when you go to your calculator, you don't have an inverse secant key. So try to remember that inverse secant is equivalent to this. Inverse cosine, because we do have a key for that, and this is reciprocally related to this, but in its inverse form, so you also have to use the reciprocal of this domain. Okay, so when we press that in, second inverse cosine, and then 1 divided by, and you get 1.80. And you can just use that as the reference angle in both of your triangles. All right, so if the angle is 1.80, that would actually be the solution to this, because when you're right here at pi over 2, that's approximately 1.57 pi divided by 2. So when you've rotated all the way to where this first hypotenuse is in quad 2, that's about 1.8, because this would be 1 pi right here. Okay, so this would be one answer, 1.8. So we could actually use this as a theta. And then what we can do is figure out what the reference angle is based on that. If they've given you 1.8, that would have to be past the 1.57 mark. And this hypotenuse is in quadrant 2, so this actually stands for the distance from 0 to this hypotenuse. So that's one of your solutions. But with that solution, we could figure out the reference angle ourselves. Okay, so let's see. This is the 1 pi location. 1 pi minus 1.8 would give you the leftover between pi and 1.8. So I'm going to go see what the reference angle is. Second function pi minus 1.8. Second function pi minus 1.8. That is reference angle of 1.34. And I'm going to use that to help me get my other answer. I want to also know where this arm is right here. So that would just be 3.14 plus this reference angle, because if the reference angle is 1.34 in this upper triangle, then it's 1.34 in this one as well. So if you rotated all the way to pi, but then rotated an additional 1.34, that would give you where this other theta is. So 1.34 plus second function pi is 4.48. And those are your two solutions using a calculator. Okay, coming to example 14, it says solve the following equation on the interval between 0 and 2 pi. So no general solutions here, but it is second degree. The other issue with this problem is that you have more than one trig function here. So you need to figure out a way to either have it as all sine squared or all cosine squared. Now, I'm going to go with all sines, everything in terms of sine, because you have more than one term that has sine in it. So let's just go all sine. We have a way of getting rid of cosine squared, and that is Pythagorean identities from chapter 6, and we'll be using it a lot in this chapter. So one of them goes like this. There are 3 Pythagorean identities concerning the trig functions, and one of them went sine squared plus cosine squared is equal to 1. Okay, so if you want to have something to get rid of this cosine squared value, just solve this for cosine squared. Let yourself see what cosine squared is by just bringing this sine squared term to the other side. So cosine squared is 1 minus sine squared. By the time you subtract sine squared from this side and subtract it from this side, it's 1 minus sine squared. That's equivalent to cosine squared. That means you can come in here and replace cosine squared with its equivalent, 1 minus sine squared, plus 1 minus sine squared is equal to 1 plus sine. Okay, so you have negative 1 sine squared and negative 1 sine squared. That's negative 2 sine squared. Those are like terms. I just collected them by way of their coefficients. Negative 1 plus negative 1 is negative 2. Then I have a positive 1 here and a positive 1 here. So if I was to try and move everything to one side, which you need to do whenever you have a second degree equation, just move everything to one side. unless you're going to use square root method like we did in one of those problems where we had a squared term and just a constant. That is not what we have here. So that means everything needs to come over to one side for factoring. So I'm going to subtract 1 on both sides, but that just gets rid of it here as well as here. I'm also going to move this sine term over here, and it becomes negative sine theta. Okay, I'm going to factor now, and what I'm going to do is I'm going to factor by a method called factoring out the greatest common factor. I'm going to divide all of this by -1 first, just because it'll make the factoring easier, leaving myself with 2 sine squared plus sine theta is equal to 0. Okay, what's common to both of these is sine theta, so I'm going to take sine of theta out, 1 parenthesis anytime you're taking out the greatest common factor. That one factor that you've taken out, the greatest common factor, becomes a multiplier that helps you get back each of these terms. So ask yourself, sine of theta times what would give you this back? 2 sine theta. And then sine of theta times what would give you that back? That would be +1. And you now have 2 factors. You have this factor that you've pulled out because you're going to make little baby equations out of each first degree expression. So take that first degree expression, set it equal to 0. You want to know, you want to get an equation made out of this factor equal to 0 and also this factor equal to 0. But at least now you have 2 first degree factors. And you want to get the solutions for each one of these equations. So when is the sine of theta equal to 0? Well, when you're talking zeros and ones being equal to the sine value, it's because you're in one of those quadrantal positions. Remember, this is 1 unit out, 0 units up. This is called the 0 location, and this back value is the sine. The front value is the cosine. So right here is where the sine value is 0, because that's not happening here. Look, it's 1 in this particular situation. When you're here, so not there, but it does work here. The sine value is also 0 at pi, at the pi location right there. At 0 and at pi, so that this gives you 2 answers, 0 and pi. Then we also want to get the solutions for this other equation. And this other equation, it's first degree, isolate that unknown. So that means we're going to pull this over here. That'll give us 2 sine theta is equal to -1. And then divide by 2, divide by 2. And you have, let me finish this up here, sine of theta equal to -1/2. You want to tell where, what locations on the circle have a sine value of -1/2. So I'll draw that right here. I'm not running out of room, but sine is the y coordinate. So you want to be in quadrants where the y coordinate is negative. That means down here and down here. Up to the x-axis, go attach this value of 1/2 on the leg that represents sine, the y value, which is the vertical leg. Having it on the vertical leg automatically tells us what the reference angle is, always associated with 1/2, the short leg, because this would be part of a partnership, 1/2 square root of 3/2. But you don't need to put square root of 3/2 here because it's this vertical value that tells you what your reference angle is. Always across from 1/2, any kind of 1/2 is 30 degrees, pi over 6. So this is pi over 6. But you want the location of the hypotenuse in each quadrant because that's the actual solution. I'm not going to number these. Okay, so where have you, if you're at 0, where have you rotated if you've gone? Mess up my drawing. Okay, so you're rotating right from 0. So 0 all the way till you get there. Well, you got to be thinking sixes. At the 1 pi mark, you're at 6 sixes. You're rotating an additional 6 beyond that. So here is a third solution. Then you're also going to keep rotating until you get over here in quadrant 4. Well, at 0, by the time you get back to 0, you started at 0, but by the time you get back there, that's 2 pi, or in other words, 12 sixes. So if you were rotating and you kept going past this first solution until you got to this next hypotenuse, that would be 11 sixes, because you're almost to 12 sixes, but you stopped 1 6 before you got there. So this other theta is 11 pi over 6. Okay, so there's 4 solutions there. 0, pi, 7 sixes pi, and 11 pi over 6. Those are your 4 solutions in that situation. Okay, let's see if there's any more. There is one more problem, and that is example 15. So this one is just a different kind of factoring, but it is also second degree. So let's see. This kind of factoring would be the same thing as, just imagine that instead of sine for your unknown, you had an x. It would just look like this. 2x squared minus 9x. If the unknown is just sine of theta, then this would be x squared. This would be your linear term, and this would be 7. So it's all a matter of whether or not you remember how to factor something like that. I'm saying let sine of theta be x. And then it looks just like, one of the problems that you had in your algebra classes where you were just factoring. So there's a few different ways that I've seen this be factored. A lot of students in my classes like splitting the middle term. And so I'm going to do it that way for you. You can always pop the sine of theta right back in there at the end after we get it factored. So here's a demonstration of splitting the middle term. You try to think of 2 numbers that when multiplied together give you a value that's equivalent to a times c. Remember, this is a, this is b, this is c. So a times c would be 14. We're looking for 2 values that multiply together to give us 14, the a times c value. But those same 2 values that you're going to come up with just by knowing your times tables, the sum of those 2 values should also be equal to -9. Not too hard to figure out. Even if you just know some really basic times tables. So 7 and 2, would that work? If you go -7 times -2, you will get a positive 14. Also, when you add -7 and -2, you get -9. So that works. And once you find these 2 values, that's how you split the middle term. Okay, so this is just a factoring technique called splitting the middle term. It is specifically used when you have a quadratic, second degree, trinomial, and the leading coefficient is bigger than 1, because that's the one that students have a hard time with. So here we go. Let's split that middle term. Leave the front term alone. Split this up into -7x and -2x. And you can even rearrange these. You could purposely put the one that you know is going to have something in common with the one in front of it. So if we rewrite this like this, probably even be better. 2x squared, not that we couldn't do it this way, but if we put it like this, 2x squared, and we put the 2x first rather than the -7x, then it's really easy to see what each of these 2 terms have in common. Because if you remember this method, that I'm talking as though you already know what the next step is, but we have taken and split this middle term. So we've stretched out this trinomial into 4 terms, and you probably remember that factor by grouping is very often used as a successful method for factoring that many terms. So that goes like this. When you do factor by grouping, it's because you have 4 terms, and you're going to group the first 2 together and ask yourself, what do they have in common? 2x in this case, and then you say 2x times what gives you that back? 2x times what gives you this back? -1. Then you're going to move to the back and ask, what do you have? What do these 2 things have in common? You can see that they have a 7. I'm going to mess around with the negatives and say that it's a -7, knowing that I want this to come out like this so that I can take out a GCF one more time. Because when you're doing factor by grouping for 4 terms, you take a GCF out once, you take another GCF out for the back 2 terms, and then you take a third GCF out for the third thing. So taking out a common factor 3 times. I'm going to mess around with -7 times x, matches so far what's in the parentheses I'm talking about. This times this would get you that back. -7 times -1 would get you that back term back. Okay, now take out a common factor one more time. You're treating this as 2 terms, one here, one here. What these 2 terms have in common is x minus 1. And then what goes in this other parenthesis to get this fully factored are these items that are out front, 2x minus 7. Okay, you can bring that right back up here. This thing's all factored, and you can pop this right back in wherever there's an x. So I did this by substitution just to make it seem more familiar to you. Okay, so instead of these x's here, I'm going to go what I allowed x to be equal to, which was sine of theta. So sine of theta minus 1. And then right here, 2 sine of theta minus 7. Okay, we're going to make 2 equations. One out of this linear factor, one out of this linear factor. So sine of theta minus 1 is equal to 0. We'll see if we can get any solutions from that. And 2 sine of theta minus 7 equal to 0. Okay, this one, when you try to isolate the unknown, sine of theta, you have sine of theta equal to 1. 0s and 1s means that you're looking for locations on the unit circle where the sine value is equal to 1. Let's go over those again. At 0 degrees, the coordinates are 1 out, 0 up. Okay, you want the sine, which is the back value, to be equal to 1. That's not there. How about pi over 2? At pi over 2, the coordinates are 0 for x, 1 for y. Perfect. So this gives me a pi over 2, and then remember that over here at pi, it is -1, 0. -1, 0 for the y coordinate. That's not what we want for our sine value. And for 3 pi over 2, the coordinates are 0, -1. Again, that is not what we want for our sine value. We wanted it to be 1. So only at pi over 2 does that occur. Let me move these solutions down here. So pi over 2 is a solution for this linear equation. Now let's see if I can get anything additional out of this situation. Again, isolating that trig word. So it would be sine of theta, 2 sine theta, moving the -7 to the other side, which would be +7, then dividing the 2 right off of there. So I would have sine of theta equal to this 3.5 right here. Not familiar with those values, so I can go to my calculator, turning this into an inverse to allow my calculator to find the angle. So the inverse sine of 3.5 is equal to theta. But you're going to see as soon as you press this in, and you may recognize this already, the domain for inverse sine is a number between -1 and 1. If you don't remember that, then what would happen is that you would just start entering it, and your calculator would tell you that this is a non-allowable value. It's not in the domain, and therefore there is no solution for this particular factor and the equation that it created, but you did get a legitimate solution out of this one. So final answer, pi over 2. And that's it for that one. Okay, that concludes all the examples for section 7.3.